And I think this kind of leads us to our next presenter, who is Pedro. And Pedro will talk about something that's like a little bit more routine, which is when you are looking at models and trying, like, say you've gone through like this whole analysis and your outcome of your project is to build a model that may be used as part of a data product or some kind of design process. Can you formalize the language and set some standards around bias measurement and fairness metrics, and kind of standardizing that so you can make it more routine? Because all the work that, you know, Molly and Chris did, that took so much time and it was so much resources and required real working together, like with the partner. And that's like a whole project in itself. But if your bias and fairness is one part of your entire project, how can you approach that? And I think Pedro's on, but just to give a little bit of background about Pedro, he is the kind of the chief architect of the Aequitas open source package. And if you go look at the documentation, it's really well done. And it gives you a pretty opinionated way of how you should do bias and fairness audits as part of a model building process. And kind of, I've been doing a bunch of talks on bias and fairness, and I've just been peddling. When, you know, people ask me how to do it, I say, just, you know, type it into import Aequitas, done. But Pedro will talk a little bit more and give us a technical tutorial on how to use it.
I can throw in one more thing before Pedro starts, just to tie it back to the theme about homes. I had a housewarming party like 2 years ago, and I moved into my condo, and Pedro brought as a gift a book of Portuguese poetry, which I still have not read because I still can't read Portuguese. But
well, hello everyone. Well, let's hope that Google can develop some real-time translation that is not biased when you translate from Portuguese to English and gender-neutral languages. But until then, thank you so much for the introduction. It's really a pleasure to be here at the Solve for Good Academy. As Arim said, this work started back in 2017 when I joined the Data Science and Public Policy Center at U Chicago as a postdoc. And Rai really challenged us about this gap between research and practice. By then, there were already many research papers about bias and fairness and mitigation and different ways of defining and measuring bias. But there was a gap on actual toolkits, on tools that people can use and seamlessly integrate in their data science pipeline, as Arim was mentioning. And this is all about that. And Aequitas stands for equity in Latin. So just to give a little bit of this overarching goal around this work on bias and fairness that Rai has been doing over the years. You know, in all these data science for social good projects, our mission is to help our partners, our organizations, to help their communities. But often our partners have limited resources. So there is this tension between efficiency and fairness and equity, in the sense that often when we are developing our data science, ML, AI, whatever you want to call them, systems to help decision making, we usually optimize for a global performance metric. And there is this trade-off that is very common between accuracy and fairness and equity, in the sense that because we have very limited resources, we need to account for how are we distributing these interventions across different groups. And in order to achieve that, it really starts really in the beginning of the project. It's really in the project scoping. So when we are discussing with partners what is the scope of the project, we must come to an understanding of what is the fairness, what are the fairness and equity goals for the project. And this is not easy at all, and this is not covered in this talk today. Today we are focusing on the second step, so on how can we systematically measure and detect bias in data science systems. And of course, there is a whole set of pipeline towards getting these equitable outcomes, from detecting, understanding, trying to improve our models, try to mitigate the impact, and keep continuously monitoring. Because as these systems get deployed over time, as there is degradation in performance, there can also be degradation in our fairness results. The same with automatic retraining of models. Are we sure that there is no shifts in the data that will introduce some sort of bias? So this is ongoing work. When we have machine learning data science systems in production, we need to continuously monitor and evaluate the bias and fairness of our systems. But first, just to get some common ground here about common misconceptions. So it still strikes me that with so many news stories about bias and fairness, there are still it's still very common to get this misconception about if we remove our sensitive attributes from the model, how can it discriminate? So how can the model be racist if it doesn't know the race explicitly when we are developing our representations of the data? Well, what happens in practice is that because we are collecting so many different signals about people, that often is very common to have different signals that are highly correlated with our sensitive attributes. So for instance, it's very easy to predict, unfortunately, it's very easy to predict ethnicity or skin color based on zip code, or based on education level, on income, or it's very easy to predict gender based on Instagram likes. So it's not enough to just remove a sensitive attribute to assume that the model will be blind to these attributes. And often we see these types of statements in the media. This one is from a large bank executive that says that there is no gender bias in our process for extending credit. We don't ask whether, when someone applies, if they are a man or a woman, we don't ask if they are married. Well, this actually introduces two types of problems. One is that they assume that because they are not using any kind of information about sex or marital status of the applicants, that the model will not discriminate against these attributes. And also, it also assumes that we should not collect this data, and if we don't collect this data, we cannot measure and we cannot detect and assess the biases against the model. So this creates a kind of a negative loop which is really about an awareness of what is going on. And I think it's really part of the industry practice that I can say that industry is somehow blind to discriminations of the models that are in production. And the second misconception is also about focus, and this is more about research community. It's on just assuming that because we develop a machine learning model that achieves our fairness goals, the system itself will produce fair outcomes. And this is very common when we are detached from real world applications, as is the case of our projects in Solve for Good Academy. We have this is the practice of real world data science, and it's not just enough to guarantee that the model is fair, because there are lots of sources of bias, and I'm going to give a few examples. But what we really care about is about people outcomes. If we think about diabetes, it's diabetes prevalence going down. It's not about our predictions that are fair if they don't produce fair outcomes. And as I was saying, there are many sources of bias. It's also very common to see this misconception in the media that AI is biased because it's garbage in, garbage out. So if you have biased data, you have biased predictions. Yes, data is for sure one of the sources of bias, but everything starts with the world, right? And data is just an artifact, and it's generated by a bias process, and we have different types of bias in the data. The machine learning pipeline, every decision we make when we are developing can introduce some sort of bias. And also the interventions and actions that are being informed by our models can also generate some sort of bias. So going a little bit deep on these sources of bias, starting with sample bias, um, it might happen that we are using a data sample that is from a different population from the population in which we are going to intervene on. And it can also be that we have not uniform quality across different groups. We can think about different geographies and different people responsible for collecting data. You can think about police officers registering demographic data about people. I know Arim knows about projects in which we have all kinds of demographic data about people that were introduced by the action takers. And this can for sure be a source of bias. Also, there is a problem of representation. If we have really few examples for specific groups, we know that machine learning is greedy, and if we have more points to train from a specific subgroup, the efficiency, the performance will be better in this subgroup than for others. Uh, Another source of bias that is probably, this is one of the most difficult source of bias to tackle, it's the label bias. If you are using triage, you know that the way we define a label on triage is through a query. So this query is defined by us, data scientists. So when we are doing project scoping and we are defining what is a label, we are basically creating a proxy variable to try to fit a model about the world and the problem that we are trying to solve. And this translation of a real world problem to a data science problem to a label can introduce some sort of bias. We can think about if you want to build a job screening, candidate screening systems, and you define promotions, previous promotions in the company as a label. If the promotions are in fact result of a bias process, and your labels will introduce source of bias. And we have the cases of over-policing and police internal investigations, for example. And because you are trying to solve these projects in the summer through data science, and you are in the role of data scientist, you are making decisions. And by making decisions, you are introducing some sort of bias, the way we store and link data. So record linkage can really introduce bias into dimensions, because you are, for instance, duplicating instances from a given group, because someone's record should be just one record in the database, but because of problems of record linkage, it's 2 or 3 records. So you are expanding and getting in a non-realistic group size for a specific group. And at the same time, you are missing feature values and you are changing the feature distribution, because some events are captured in a given entry on your database, and other events are on either entry, and they all should be part of the same row, let's say. And the way you define metrics, what are you optimizing for, the hyperparameter space you define, how you evaluate and select, how you deploy and maintain, all of these steps, all that is a part of a human decision making is introducing some sort of bias. And then there is also the action intervention bias, because in these data science for social good projects, we often have a human that is being informed by the model. So the model, fortunately, is not making decisions automatically. So we have a human in the loop, and the human receives the recommendation from the model and needs to make the final call. And the way the model predicts and by being specific about certain attributes, that can open a backdoor for the human in the loop to override decisions in predictions of the model for specific subgroups and not for others. And also there is for sure a problem that is very hard to tackle, which is the heterogeneous treatment effects across different groups. So we believe our interventions will be equally effective across different groups, but it might be the case that we need tailored interventions for specific subgroups. Then moving on from sources to definitions of fairness, there is no universally accepted definition of what it means for a decision-making model to be fair. And this is actually what was the central point of the whole discussion about ProPublica and Compass. So Compass run this audit on, ProPublica run these audits on Compass predictions, and they found out that the false positive rate for African Americans was almost twice as a false positive rate for Caucasians. And North Point, that is the company that developed Compass, replied back saying then that they are aware of that, and that is a design choice because they are optimizing for precision parity, which means that when a judge receives a score, the score should have the same likelihood of being correct across different groups. And then we might end up in these rabbit hole discussions about what is fair, what means to be fair. And in fact, there are so many different definitions and so many different metrics that can be used to define fairness, that when we interact with an organization as our partners in data science for social good projects, this can be very overwhelming for a non-technical person to come up with a specific definition of what it means to be fair. In fact, this is a traditional example of all the metrics we can get based on the confusion matrix. In fact, all these metrics can be used as bias definitions and can be used to calculate disparities and to assess fairness. So it is very hard to navigate through all these metrics, and often is the case that there is incompatibility between some metrics. For instance, and this is a well-known result, it's actually very easy to prove if you want to try it, is if you have different groups and these groups have different prevalence, you cannot achieve at the same time precision parity, which is this false discovery rate, because false discovery rate is 1 minus precision. You cannot achieve at the same time precision parity across groups or equalize odds, which means equal false positive rate across groups and false negative rates across groups. So there is this theoretical incompatibility that is rooted in the confusion matrix. So we cannot achieve all these metrics, but maybe we actually don't need to achieve all these metrics. So work that we have been doing is on creating this fairness tree, which is a framework, can be seen as a framework. Our idea is not to be too prescriptive, but is more to help our stakeholders, our partners, to navigate through all these metrics that are possible to choose, and by answering specific questions to narrow down the range of possibilities. So we really start our roots. The most important question is, are our interventions punitive or assistive? And this is really changes the types of errors you care about. Because if they are punitive, the cost or the harm is based on false positives, because you are in fact giving a punitive intervention for people that actually are, let's say, label negatives. They don't deserve this punishment. But if your interventions are assistive, you really care about type 2 errors. So are you missing people that need help? And are you missing people disproportionately across different subgroups? So then there are specificities, because most of our projects at the SSG are assistive. the interventions are helping people through personalized healthcare, to personalized outreach, mental health outreach on criminal justice system problems, and so on. And then it's more about how much do we have to spend on interventions? So what is our capacity? Are we intervening in a very small fraction of the population, or are we intervening in most people? So for instance, in a project that I worked on diabetes screening, we can provide the diabetes screenings to a large portion of the population. But in other projects, for instance, criminal justice systems, we have a very limited capacity of intervention. So in that case, probably the best fairness metric to choose is recall parity. But fairness tree is not the answer, in the sense that uh, defining a fairness metric is probably the most difficult thing to do when auditing and assessing and measuring bias. So it's more about, you know, kickstarting a conversation between data scientists, between the policymakers, between the communities that are affected by these decisions, and trying to come up with a consensus on what fairness and equity means in a specific project. And for sure, this really depends on intervention, as I mentioned, and on the stakeholder values and on geographies, on specific community needs. We, as I mentioned in the beginning, we are focusing on the second step on this fairness agenda. And the audit paradigm is really, what I said in the beginning, something that Raid was thinking about is, you know, if we cannot have a tool or tools that can get us easily bias results or bias audit results, we cannot improve bias. And this is the old cliche from Lord Kelvin: if you don't measure, you can't improve it. This is really cliche, but it's actually what happens in this case, because if, as I said in the beginning, these large banks, they are not aware of the large banks and large insurance companies, if they are not aware of the biases of the systems, they cannot really fix the problem. So it's really about creating awareness among stakeholders, and this will for sure helps promoting bias and fairness as a main KPI of the projects. And by measuring it, we can optimize bias mitigation techniques, and we can really define tailored mitigation plans for our specific projects. So that's why we developed Aequitas, our bias and fairness audit toolkit. Since we released Aequitas in 2018, thankfully, there has been more of these toolkits in this area of bias and fairness that were launched. There is from IBM, there is from Microsoft, from Google. And the case of Aequitas is more tailored for this kind of social good public policy problems. And this really started with this kind of a vision. We actually never implemented this report, but this is inspired on legal kind of audits. And it's kind of saying what was the project goal, what was the performance metric, the bias metrics considered, reference groups, what was the model that was audited, what were the results, what is the performance, and this is kind of a model sheet. As we have seen recently, there is model cards and other groups of people propose different ways of providing this sort of information, which I think is really great, and the community is really evolving in the right direction. So how can you use Aequitas? You can use Aequitas through a web audit tool, and this web audit tool is more tailored for non-technical people because it's more on point and clicks, and is limited. You need to upload data, and you define a set of parameters, and you get results. The Python library, which I believe is the to-go way for you working on the Solve for Good Academy. And there is also a command line tool, which is also very handy when you want to automate the process of auditing and you want to add thousands of models for different thresholds and so on. So how Aequitas can be used in the larger pipeline. So our vision is that Aequitas should be used by the data scientist when evaluating and selecting models, but also by the policymaker before accepting a model. For instance, before you transfer the models you developed in summer to the partners should audit the models themselves, and they should make the decision about deploying based on the audit results as well. And as I said in the beginning, this is an ongoing process, and even when the machine learning models in production, audits should be continuously carried. So what you need to audit the model? You need predictions, you need the attributes that define the protected groups, and you need the labels. And the workflow for the data scientists mostly this: you build models, you audit, you take care of any kind of mitigation approach you might be able to do, from resampling to trying different algorithms that have some bias regularization parameters, to some kind of thresholding as post-processing, and you try and you have this loop until you are happy with the results, and then you move on to the next stage. And then you can have this paradigm, the audit paradigm, in which beforehand you pick a model based on a single performance metric, but as soon as you run Aequitas and the audits, you unfold a new dimension, and now you can compare models not just on performance but also on bias, and then maybe you can sacrifice a little bit performance and you can pick a model that is slightly less biased. It really depends on your fairness goals. However, as every stage, every step of the machine learning pipeline in which a human is making decisions, as I said in the beginning, you are also making some sort of decisions when you're running the audits. You need to define global threshold, you need to define what groups, you need to define what are the metrics. And Aequitas, by relying on the labels, it's really agnostic to the problem of label bias, because you are using the labels to calculate these confusion matrix metrics, and if the labels have some sort of noise that is not uniformly distributed across different groups, imagine that you have for a specific minority, the labels are very noisy, the audit results will be based on these noisy labels. So this is probably the most striking weakness of Aequitas. Also, it's sample specific, so it really depends if you audit for 1 week of predictions, for a month of predictions, for 3 months of predictions, the results might vary. So this is really how you define your frequency of audits. And also because it's not errors are the same, and not all disparities are the same. If you are talking about, for instance, assistive intervention, maybe having higher true positive rate than a group is not really a bad thing for the group. It's really about how are these different disparities taken into consideration. So now just a few minutes on a specific case study. So this was a DSSG 2018 project. Partner was Alliance Chicago, and the goal was to prioritize early diabetes screening. And the label is if when you visit a doctor, if you develop diabetes in the next 3 years, that's a 1. And if you don't develop a diabetes, that's a 0. And this is a case study on fairness aware model selection. And our performance metric is we call it K. Our group metric for bias, in this case, we opted for false omission rate, but we could have gone with chosen the recall parity. Protected attributes is age, race, and sex. And the test set is 200,000 patients that visited a doctor during 2014. And there is a 3% prevalence. So 7,000 diagnoses in 3 years interval after the visits. So here we started with auditing the current practice. It's very tempting to start auditing our models, and we don't audit the current practice. So this is actually the baseline, right? So the medical doctors making decisions about screening, this is the baseline. So we started to audit the current just human experts decision-making process. And we found out that for race, there was some higher false omission rates for Native American, Native Hawaiian. And then we developed a bunch of models, hundreds of models. And as you can see, this is the performance metric. And there is a good trend here in the sense that as we get better performance, these group-wise false omission rate also gets lower. Although the disparities, we still have different disparities even in the highest performance models. So we need to dive in for specific models to understand here what are the disparities. So here we have the model with the highest recall, so the model with highest performance, and we are comparing, this is the orange one, and we are comparing with the blue one, which is the baseline human based on the doctor's decision process. And as we can see, this is much better in terms of global performance, but also in terms of individual group metrics, we have better false omission rate for all individual groups that we care about. However, compared to the current practice, here I don't have the numbers, but the max disparities across the human expert were actually lower than the max disparities across the new model. And then we went for what is the model that has the lower range across different disparities, the different false omission rates across different groups. And this is the mustard model. So the mustard model is still better than the current practice on every group defined by race, but is slightly worse than the most efficient model, because this one is really the model that has less disparities across different groups defined by race. So now the question is, the tension. Are we going for full efficiency? So we want to help most people that actually need help. So people that will develop diabetes in the next 3 years, sorry. Or should we sacrifice? So it means that we will not be able to help so many people in absolute numbers, but we have a much more fair distribution of help across different groups. So that's the tension. And that's why it's so important to have informed conversations with stakeholders to reach a decision. But this is for a given specific test set on a point in time. But what happens over time? What happens over time is that if we believe that this is a hypothetical example of the diabetes prevalence of two groups, so in this case, two disjoint groups, non-white and white, and you can see that based on current practice, there is this gap of the diabetes prevalence. And now we start our intervention. So we now deploy a machine learning model. And we can see that the slope is good for both groups in the sense that our interventions will help reduce diabetes prevalence over time. But what is happening? The gap between the groups is widening over time. And we will end up in a point in time in our society in which we have a huge gap between white and non-white populations. Even an extreme case, once again, this is hypothetical, in which we don't longer have diabetes for white population, but we still have the problem of diabetes becomes a disease just for non-white people. So maybe because we have this historical disadvantaged group, we might tailor our interventions for equity in the sense that we will try to close the gap between the groups first, and then we will try to reduce the overall problem. And this is just one possibility to consider. So the main takeaway message is that audit for bias and fairness is really a first step to create awareness. And if you audit, and this is a systematic process that every machine learning model you develop, as you evaluate the global performance, you also audit for bias and fairness, then you can inform a wide range of downstream decisions that you make throughout the project, meaning that you can define specific samples, you can try different mitigation approaches, you can automate some sort of this mitigation process, you can have informed discussions with your stakeholders, and hopefully you this is a small step on this larger agenda of developing AI that results in fair and equitable outcomes. Also, there is this overview on bias and fairness, this chapter book of big data and social science. The book is not, the second edition is not released yet, but it's already accessible through this online version. So please ever read. Most of what I talked today is explained there in more detail. So that's it.
Pedro, thank you so much for a great presentation. I also learned something new as I went through this for, the third or fourth time. So this was super helpful. And just to kind of wrap up for today, we'll post all the links and the recordings and communicate that with everybody on the chat. And thank you, everybody, for tuning in. And I think that's all we have for today.
Yeah, if you take away one thing from this whole session, I hope that it's all about people and poems. And please join us next time for our session on implementation and project handoff. That's featuring some shares from our partners at DSSGX at the Turing Institute, as well as Erica Solomon from Medic Mobile, one of our partners, and Nick Hamlin from Global Giving. Thanks so much, everyone, for joining.
Thanks, everyone. Bye.
Thanks, everyone. And I wrote a closing haiku poem for everybody.
Please share.
Please share your haiku.
Here it is. Thank you for coming to the session on being fair. So good it was numbing. All right. Luckily, everyone's left.
Thanks, everyone. Bye.
Okay. Thanks, everyone. Bye-bye.